Hi everyone, I'm Harsh Mahajan and I'm currently a student at BITS Pilani pursuing computer science and engineering. Today, I'm going to be presenting the Fantom platform to you and giving you an overview of the Lachesis consensus protocol and Opera platform that make the Fantom platform possible. What exactly is Fantom? Fantom is a high performance, scalable, and secure layer 1 platform built on a permissionless, asynchronous Byzantine fault tolerant consensus protocol. By the end of this talk, you will be able to understand what exactly does this definition mean. So Phantom has been designed to solve the blockchain trilemma. For those of you who are not aware, the blockchain trilemma states that in any blockchain-based technology, one of the following factors is always going to be compromised in order to have the other two factors. For example, when it comes to current proof of work cryptocurrencies like Bitcoin or blockchains like Ethereum, we can clearly see an emphasis on decentralization and security. However, scalability is a huge issue because of which both of these cryptocurrencies have still not seen widespread adoption. An example for why exactly are all of these three features very important in any blockchain technology are decentralized finance applications. These applications are competing with traditional centralized financial systems, which are able to provide a considerable speed along with negligible transaction fees. We can take the example of UPI here, where one is able to transact any amount between parties and effectively faces no transaction fee. The amount gets instantaneously credited from one bank to the other. Now, in contrast to this, we can take the example of Ethereum. In Ethereum, it takes around 15 minutes for a transaction to be finalized in the first place. And then, because of the clogging up of the blockchain, the transaction fees in the first place is growing exponentially. This effectively leads it impossible to transact on the Ethereum blockchain using, I'm sorry, for small and meager amounts. All of these problems will effectively lead to there not being a decentralized financial technology being widespread. And thus, a solution for the blockchain dilemma is desperately needed. As we can see, the key features of Phantom are its speed, its low fees, which are almost negligible, as well as the fact that it is compatible with EVMs or the Ethereum virtual machine, which allows for applications written for Ethereum to be very easily ported over to the Phantom platform. Now the focus of the talk is going to be about how exactly does Phantom achieve all of these features, and the answer to that is the novel architecture that it uses. This architecture consists of the consensus mechanism as well as the middleware. The Phantom team basically had certain design considerations in mind, which were being able to support high volume of transactions, being able to make sure that execution was instantaneously precise and not based on probabilistic consensus, and also to ensure interoperability of Phantom with the other blockchains like Ethereum. Hence, the team proposed Lachesis as their consensus mechanism. And the major features of Lachesis are is that it's asynchronous, it's fast as well as inexpensive, it is very secure, as well as it is leaderless. Thus, Lachesis effectively claims to solve the blockchain trilemma. On top of Lachesis, the Opera platform is built. The Opera platform allows Phantom to be interoperable with the Ethereum virtual machine, which allows for instant deployment of smart contracts that are already written in Solidity. Thus, developers don't need to learn a new technology in order to be reaping the benefits of Phantom in the first place, nor do they have to spend the time to uh, create new code. And lastly, at the application layer, keeping in mind the spirit of decentralization, the Phantom platform is able to support decentralized governance, smart contracts, as well as DApps. Before we talk about Lachesis, we need to first have an overview of what is the goal of a consensus protocol, what are the design choices that developers have to make when creating a consensus protocol, and how exactly do we measure the performance of a consensus protocol. So, as you can see, the goal of a consensus protocol is to achieve a finalized same order of transactions on honest nodes, even in the presence of offline or malicious actors. Consensus protocols are super important when it comes to any distributed system, especially when it comes to blockchain based technologies. Consensus protocols make sure that without trusting any single party, you are able to verify whether a particular transaction is valid or not. Coming to the design choice that has to be made when developing a consensus protocol. A consensus protocol can either be prioritizing finality or consistency, or it can be finalizing liveliness or availability. Now, what exactly do we mean by finality and liveliness? Finality indicates the speed with which a consensus protocol is able to finalize a transaction after it has been initiated. It measures the effective time taken from for the user from the user initiating the transaction to the transaction being verified and showable on the blockchain. Liveliness, on the other hand, deals with how available the system will be in case of there being a growth in malicious actors or in case of certain nodes going offline or becoming inactive. And there is a trade off between finality and liveliness. For example, Bitcoin, because of its proof of work design, is optimized for liveliness, which makes sure that even if there is a single node operating on the network, it is able to perform its job. Whereas Phantom is prioritized for finality. Bitcoin, for example, takes around 30 to 60 minutes for a transaction to be processed, whereas Phantom takes only a couple of seconds. Now, how exactly are we going to be measuring the finality of consensus protocols? There are two methods to do this, two metrics that is. One is TPS or transactions per second, and the other is TTF or time to finality. So TPS basically measures the number of transactions that the distributed system is able to handle in a system in a second, sorry. Whereas TTF basically tells how long a user has to wait on average until their transaction gets finalized and is shown to be finalized on the blockchain. There is a trade-off between TPS and TTF, and thus there is a delicate balance that needs to be maintained between both of them in order for scalability as well as speed to both be present in the system. Finally, coming to Lachesis. What exactly is Lachesis and how is it able to achieve this finality? Lachesis is a proof of stake directed acyclic graph based asynchronous Byzantine fault tolerant consensus algorithm. Let's go over this definition one by one. Lachesis employs proof of stake. So, the validation power of any validation node is based upon the amount of phantom that has been staked on that node. And proof of stake in general ensures that if a node decides to behave maliciously, the staked token itself gets deducted or burnt, which results in the malicious actor having a huge disincentive from committing anything. The second term in the definition, a DAG or a directed acyclic graph. A directed acyclic graph is basically nothing but a graph in which there are no cycles present. For example, here we can see that Lachesis in Lachesis the events are not ordered according to the time taken in a robust ordered manner. Instead, they are loosely ordered on, and modeled like a directed acyclic graph. So events are connected using a happened before relation. So event A will be connected to event B if and only if event A happened before event B. As can be seen on the figure in the right, unlike a blockchain where there is only one connection from one block to the other, these events can have multiple connections coming into and going out of them, which provides it with an approximate order. However, this DAG can be used to then calculate the exact final order of events on every single node once events have been appropriately confirmed by different nodes. That is, at least two-thirds of the participating honest nodes. So, in order to communicate between nodes, Lachesis employs a gossip about gossip protocol, where nodes pass events to each other. They may be events that have been created on the node itself, or they may be events that they have heard effectively from other nodes. And because of this, it it is possible for the message to be shared with every single node in the network efficiently. Finally, in order to allow for a change in the validators, Lachesis groups these DAGs as a series of epochs. What this allows is that after a stipulated amount of time or after any event has happened, for example, the detection of a malicious node, the current DAG is stored as an epoch. Uh, Appropriate changes are made to the network, and then um, a new epoch is started with a new DAG. Epochs are connected one with each other, which allows them to basically have ordering. So what Lachesis effectively is able to do is using a DAG and using the gossip about gossip protocol, every single node is able to asynchronously calculate what is supposed to be the exact final order of events. And this is effectively the reason for its amazing performance. As I was mentioning, the reason why Lachesis is so successful is because it is leaderless. So, unlike conventional proof of work or even proof of stake based systems, where for every iteration one of the nodes is elected or rather chosen as a leader, there is no need for that in Lachesis. The reason being that it is asynchronous, and every single node has the freedom to emit events at any arbitrary time. and computation is happening simultaneously on all the nodes. The third feature of Lachesis is the fact that it is Byzantine fault tolerant. And this is where we come up to the BFT part of the definition of Fantom in the first place. So, a Byzantine fault tolerant system is one where if even if the presence of malicious actors is ascertained, the system will still be able to effectively communicate what messages need to be communicated to the honest nodes. The example that is given to explain this concept is the Byzantine generals problem. Consider that there are different generals with their armies surrounding a city, and they are all meant to attack the city. If, for example, we have even a few generals who end up sending wrong information, or if their information ends up getting lost due to unreliability of the messengers, and they end up not attacking, the other generals will attack and will still result in the defeat of the overall army. So, how exactly do we solve this Byzantine generals problem and make sure that our consensus algorithms are Byzantine fault tolerant? So, as can be seen in Lachesis, the calculated order is the same for all honest nodes if more than two-thirds of the validating power is being honest and agreeing upon it. However, if, for example, less than more than one third of nodes decide to be dishonest, the system stops being Byzantine fault tolerant, which is the trade off between liveliness and availability that was being mentioned earlier. So, effectively, a supermajority of nodes is required in order for there to be consensus. Thus, for all of these reasons, Lachesis has a supremely low TTF or time to finality. So here we discuss the Phantom Opera platform, which is built on top of Lachesis. So this provides blockchain nodes which are compatible with EVM, as we were discussing before. Ethereum projects are easily forkable onto the platform, and the developers of Phantom have provided various developer incentives to developers, because of which there is a widespread adoption of Phantom as well. In order to ensure that the security of the network is emboldened, there are staking rewards for delegating Phantom to validators that users of Phantom get if they decide to lock in their Phantom for proof of stake. So now, finally, we will be discussing the overall architecture and how all of these pieces come together to create the Phantom platform. So, as you can see, the different nodes which are getting different colors correspond to the block that these event nodes are going to be associated with. So, the yellow nodes here, for example, are going to be associated with block 3. The orange nodes are going to be associated with block 5, and so on. And this ordering is effectively carried out by Lachesis, which enables there to be one standard one standard ordering across the different nodes. As we can see here, that in order to make sure that we can remove validators, after a certain time, a new epoch gets created. So as we can see, all of these event blocks are then clubbed together and made into blocks, which effectively becomes the state of the particular node. Then this state is fed into the EVM, which effectively allows for Ethereum based smart contracts to be run on Lachesis too. So, with that, I would like to end this talk, and I hope that you guys were able to get uh, an overview of Lucky Sis and of the Phantom Opera platform. In case you want to dive deeper into the technical details of it, you guys can follow the references mentioned above. Uh, so thanks a lot for hearing this, and I hope you find this seminar talk insightful.